If you care about performance, you need to stop thinking about memory as storage. Real performance starts when you understand how memory actually works. Because when you do, you don't just optimize memory, you control it. Let's start with the fastest memory management technique. Looking at this simple code, how does the program know at what function to return after function B finishes? When a program runs, the system sets aside a special region of memory called the stack. Each time a new function is called, a stack frame is pushed on the stack. That frame contains things like function parameters, local variables, and return addresses. The last function called is the first one to finish. That's why the stack works in a last-in, first-out order. Because of this strict last-in, first-out structure, the stack memory is fast and predictable. There is no need to track free memory. It is assigned sequentially. There is no fragmentation. Memory is released in reverse order, and there is no manual cleanup. Everything is automatically cleaned when functions return. If you think it's too good to be true, you're right. Because the stack has some trade-offs. We are limited by size. If we try to put too much on the stack, our app crashes with a stack overflow. And we can't allocate memory dynamically, so we lose flexibility. But when declaring a new variable inside a function, not everything stays in the stack. When we declare a local variable, two things are involved. The variable itself, the reference or the pointer, which is stored in the stack, but the actual data that the variable points to is stored in the heap. The heap is a region of memory designed for dynamic allocation, large data structures, and data that live longer than a function call. Unlike the stack, which is tightly managed and automatically cleaned up, the heap is free-form. We can allocate and free memory in any order. That makes the heap extremely flexible. If we need information that live longer than a function call, or if we need large data structures, the heap gives us the freedom to do it. But this freedom comes at a cost. Heap memory is slower to allocate because the system has to search for available space. Over time, memory can become fragmented, as our data can get broken into smaller chunks, making allocation even slower. And unlike the stack, heap memory doesn't clean itself up. We either free it manually or rely on a garbage collector. And if we don't manage it correctly, we end up with memory leaks. No matter what language we use, the stack gives us speed and the heap gives us flexibility.